Hello everyone. We will now continue our lecture on the energy balance for open systems, in particular now for steady-state energy balances. Recall that we have previously derived this energy balance for open systems, and we can now make the necessary simplifications for a steady-state process. And for a steady-state process, there should be no rate of accumulation of energy within our control volume. Therefore, for a steady-state process, this term should be equal to 0. Thus, at steady state, delta m dot h plus delta u squared over 2gc plus zg over gc in any flow stream is equal to q plus w. And assuming negligible kinetic energy and potential energy for different steady flow equipment, you can have the following energy balance equation. So now, what are these different steady state flow equipment that are commonly found in the chemical process industry? Okay, so the first common steady flow equipment are what we call your heat transfer equipment. So these encompass heat exchangers, your boilers and condensers, as well as your chemical reactors and furnaces. Now, in most of these equipment, there's typically no shaft work. There's no rotating shaft or motor inside these equipment. Thus, shaft work is 0. And the magnitude of enthalpy change is so great that potential kinetic energy changes of the flow streams are negligible. So thus, in most of these cases, the energy balance equation will just reduce to delta H is equal to Q for these types of equipment. The next type of equipment are your turbines or your expanders. And turbines and expanders are work-producing equipment. They take kinetic energy or thermal energy from the flow stream and convert this into useful mechanical energy. And then this mechanical energy runs a generator which can now be used to generate electrical energy. Now, most often, turbines and expanders operate adiabatically and Q is 0. And typically for steam turbines, PE and KE are negligible. So for steam turbines, delta H will just be equal to W. The next type of equipment are your fluid motive devices. So you have fluid motive devices for compressible fluids, your compressors, fans, or blowers, and fluid motive devices for incompressible fluids, mainly liquids, for pumps. So these types of equipment are work requiring equipment, thus the shaft work is greater than 0. And typically, within the inlet and outlet of your compressor, fans, blowers, or pumps, there's typically a negligible PE and kinetic energy change, and most often they are adiabatic as well. The next type of steady flow equipment are your throttling valves. And throttling valves produce a large amount of pressure drop without involving any work. So essentially, what you are doing is you're passing through a high pressure liquid or a high pressure fluid through either adjustable valve, a porous plug, or capillary tube, and this will reduce the pressure. Now, there is no heat transfer involved. Okay? There's only a pressure reduction. However, the temperature may change, and this will be governed by the Joule-Thomson coefficient, which will be discussed later on this semester. However, for energy balance purposes, there is a negligible potential kinetic energy change, there is no heat transfer, there is no shaft work. Meaning, based on the energy balance itself, delta H will just be equal to 0, meaning we have an isenthalpic equipment. Therefore, H2 is equal to H1. So enthalpy at this point is equal to enthalpy at this point for a throttling valve. Last but not least are your nozzles and diffusers. And nozzles and diffusers generally operate for the energy conversion between enthalpy and kinetic energy change. So the main difference between the two are nozzles increase the velocity of fluid at the expense of pressure, and the diffuser increases the pressure of the fluid by slowing down the fluid. So you now have a conversion between enthalpy and kinetic energy. So essentially, the energy balance equation, assuming that there is negligible heat transfer and there is a negligible shaft work, you will have delta KE plus delta H is equal to 0. With that, let us now proceed to some examples for energy balances for open systems. So let's consider first the operation of an adiabatic turbine. So steam flows steadily through an adiabatic turbine. The inlet conditions to the steam are 4 megapascals, 500 degrees Celsius, and 80 meters per second. And the exit conditions are 30 kPa, 92% quality, and 50 meters per second. If the mass flow rate of the steam is 12 kilograms per second, determine A, the change in kinetic energy, B, the power output of the turbine, and C, the turbine inlet and outlet diameters. Given the following steam table properties. Okay, with this, we can draw the schematic diagram of a turbine. Ayan. So this is state 1 and this is state 2. So inlet conditions, then state 1, exit conditions are state 2. So unahin natin ngayon, for start solving, get the stream properties. So usually you need to get the specific volume of the inlet and outlet and the specific enthalpy of the inlet and the outlet. Starting with the inlet conditions. So inlet conditions, steam at 4 megapascals and 500 degrees Celsius. So we can read from the superheated steam table, this is now V1 and this is now H1. So V1 is 0.08644 meter cube per kilogram and H1 is 3446 kilojoules per kilogram. Now for the outlet conditions, we are given that we have the turbine outlet is 30 kPa with 92% quality. Thus, if you have 92% quality turbine outlet, it means you have a mixture of saturated liquid and vapor. So the specific volume of the turbine outlet is between these two values, and the specific enthalpy of the turbine outlet is between these two values. So calculating, you will get the specific volume of the turbine outlet and the specific enthalpy of the turbine outlet as well. Now to calculate the change in kinetic energy, this is simply equal to m dot times delta U squared over 2gc multiplied by the mass flow rate. So the mass flow rate is 12 kilograms per second, outlet velocity 50 meters per second, inlet velocity 80 meters per second, divided by 2gc, which is equal to negative 23,400 joules per second, or negative 23.4 kilowatts. Next, to calculate the power output, let's proceed to the actual energy balance equation. So for the energy balance equation, again, for a steady state open system problem, delta MHUZ of the flow stream is equal to Q plus W. Now, let's assume first that potential energy is negligible. So this will be equal to 0. And there is an adiabatic turbine, thus Q dot is 0. Now, for calculation purposes, let's not assume yet that the kinetic energy is negligible. So this will reduce to m dot u2 squared minus u1 squared over 2gc plus h2 minus h1 is equal to the shaft work. And substituting the necessary values, and take note that the units of the kinetic energy change in natural units here are in joules per kilogram. So you have to convert it to kilojoules per kilogram. So ingat lang talaga lagi dito kasi yung enthalpy typically naka-kilojoules per kilogram lagi. Okay, pero yung kinetic energy and potential energy naka-ano yan, naka-joules per kilogram. Okay, so make the necessary conversion to get the required shaft work. And solving the energy balance equation, you should now be able to get the shaft work is negative 12,122.16 kilowatts. So obviously, dapat negative yung shaft work since this turbine is a work-producing equipment. Now, in our calculation, we did not assume that kinetic energy is negligible. So what if we assume that kinetic energy is negligible? So assuming kinetic energy is negligible, the energy balance equation will simply reduce to m dot delta H is equal to the shaft work. And calculating, so you can see, the shaft work is negative 12,098.76 kilowatts. So there is a slight difference, but the magnitude is not appreciable compared to the scale of the power output. So, safe to assume naman na medyo negligible talaga yung kinetic energy change for steam turbines. For hydroelectric and wind, di talaga. Pero for steam, definitely, you can assume that delta H lang yung shaft work. And lastly, let us now calculate the turbine inlet and outlet diameters. So to do this, we need the continuity equation. So the continuity equation in this case is the mass flow rate, which is equal to 12 kilograms per second, is equal to U1 A1 over V1, which is equal to U2 A2 over V2. Okay, we have previously determined V1 and V2. So U1 and U2 are given tayo ng mass flow rate. Let's calculate individually A1 and A2, where A is pi over 4 d squared, assuming we have a circular cross-sectional area. So calculating this, 12 kilograms per second is equal to the following. And we can calculate D1 to be 0.128 meters, and D2 is 1.212 meters. So typically, the inlet of the turbine is much smaller compared to the outlet of your turbine. Kaya minsan tawag din sa kanila expander because the gas will expand or the steam will expand inside the turbine producing work. Okay, for our next example, let us consider a mixing problem. So in steam power plants, open feed water heaters are frequently utilized to heat the feed water by mixing it with steam bled off a turbine at some intermediate stage. Now consider this open feed water heater that operates at a pressure of 1000 kilopascals. Feed water 50 degrees Celsius and 1000 kPa is to be heated with superheated steam at 200 degrees Celsius and 1000 kPa. In an ideal feed water heater, the mixture leaves the heater as saturated liquid at the feed water pressure. With this, determine the ratio of feed water to the superheated steam. So, ang feed water natin dito is stream 1. This is our feed water. And ito yung steam natin, si stream 2, to produce our saturated liquid, which is then fed to the boiler. Okay. So, this mixing occurs isobarically, and most mixing process should actually occur isobarically. If there is a change in pressure somewhere here, usually magkaka-backflow ka. Okay? Or kailangan talaga lagi isobaric ang mga mixing processes. Now, for calculation simplicity, let us assume that only the temperature affects the enthalpy of this feed water stream. So, the temperature, 50 degrees Celsius, so assume natin the enthalpy of the feed water heater is equal to the enthalpy of saturated liquid at 50 degrees Celsius. So, gamitin natin enthalpy ng feed water heater is 209.34. Enthalpy naman ng steam, based on the steam table, at 200 degrees Celsius is 2828.3. And then, for saturated liquid at 1000 kPa, you have saturated liquid, ito yung specific enthalpy niya. So now, let's proceed to the energy balance. And for the energy balance, let's make a few assumptions. So, neglect natin si potential energy and kinetic energy change. Okay, since mataas yung mga values sa enthalpy, so we can assume na negligible yung change in PE and KE. Mixing process, so there should be no shaft work. Now, the mixing will also occur adiabatically, meaning there's no heat transfer palabas ng feed water heater natin. So, nagkakaroon na tayo ng heat transfer sa loob, pero walang lumalabas na heat dyan. With that, mass balance muna tayo. Mass balance natin, M1 plus M2 is equal to M3. And let's take a basis of 1 kilogram per second of product. Okay. For our energy balance now, summation of all MH out minus summation of all MH in should be equal to 0. So, lahat ng MH out ay si stream 3 lang. Ito lang yung MH out. And M dot H in, itong dalawa, M1 and M2. So our energy balance equation should simplify to M3H3 minus the sum of M1H1 plus M2H2, which should be equal to 0. And solving this, you have a system of two equations and two unknowns. Using a basis of 1 kilogram per second of product, you should get that M1 is 0.788 kilogram per second and M2 is 0.2112 kilograms per second. Thus, the ratio of feed water to superheated steam is M1 over M2, which is now 3.73. And that's it for the energy balance for open systems. If you have any questions regarding this lecture, please contact me immediately. Our next lecture will now be energy balances involving heat effects, specifically sensible, latent, and heats-off reaction.